Let us begin slowly with a familiar thought. When we first study abstract algebra, we often begin with groups. A group is a world with one operation. There is one way to combine two elements. We may think of addition, or multiplication, or composition of symmetries. The group axioms tell us that this one operation is organized, reversible, and stable. Groups are very powerful. They capture symmetry. They capture motion. They capture many forms of structure. But if we want to describe ordinary arithmetic, one operation is not enough. The integers, for example, are not merely a group under addition. They also have multiplication. And multiplication interacts with addition in a very special way. We can add numbers, we can multiply numbers, and multiplication distributes over addition. This interaction is not an extra decoration. It is one of the central features of arithmetic. So, as we move from group theory into ring theory, we are not abandoning groups. We are enriching the picture. A ring is, in a common broad sense, a mathematical system where we can add and multiply. Addition behaves very regularly, much like it does for integers. Multiplication also behaves in an organized way, though not always as nicely as addition. And most importantly, multiplication and addition are compatible through the distributive law. This is the first idea to hold gently in mind. A ring is a place where arithmetic can happen. Not necessarily all familiar arithmetic. Not necessarily division. Not necessarily commutative multiplication. Not necessarily every pleasant property we know from the integers. But enough arithmetic that we can meaningfully speak about sums, products, powers, factors, and equations. The integers form a ring. Polynomial expressions form rings. Square arrays of numbers form rings. Functions can form rings when we add and multiply them pointwise. Modular arithmetic gives us rings. Many objects from algebra, number theory, geometry, and analysis are naturally ringed. So ring theory is a language for generalized arithmetic. Let us pause and reflect on that phrase. Generalized arithmetic. That is what a ring is meant to capture. It allows us to take the ordinary behavior of whole numbers and ask which parts of that behavior are essential, which parts are accidental, and which parts can be transferred to more abstract settings. In the integers, if a product is 0, one of the factors must already be 0. In some rings, this remains true. In other rings, it fails. In the integers, every number can be factored into primes in a unique way. In some rings, a similar fact remains true. In other rings, it fails. In the integers, ideals are generated by single elements. In some rings, that remains true. In others, it does not. Ring theory asks us to notice these differences carefully. It asks us not merely to compute, but to understand what makes computation possible. Now let us begin with basic structure. A ring consists of a set of objects together with two operations. We may call them addition and multiplication because we want to think arithmetically. Addition is the more orderly operation. Under addition, the ring behaves like an abelian group. That means we can add elements. Addition is associative and commutative. There is an additive identity, and every element has an additive inverse. In ordinary language, addition in a ring behaves the way addition should behave. There is a zero element. Every element has a negative. We may rearrange sums without changing the result. We may group sums without changing the result. Multiplication is also associative. If we multiply three elements, it does not matter which multiplication we perform first. But multiplication may or may not be commutative depending on the kind of ring we are considering. In many introductory examples, such as integers or polynomials, multiplication is commutative. In matrix rings, multiplication is not commutative. That is an important warning. Ring theory is broad enough to include both possibilities. And then there is the bridge between addition and multiplication, distributivity. Multiplication must distribute over addition. If we multiply something by a sum, we get the sum of the separate product. This is what allows algebraic expansion. It is what makes expressions behave coherently. Without distributivity, addition and multiplication would live side by side without truly communicating. It is worth repeating this slowly. A ring has addition. A ring has multiplication. Addition is highly regular. Multiplication is associative and sometimes commutative. And multiplication distributes over addition. That is the basic shape. Now, within a ring, we often find smaller rings. These are called subrings. A subring is a smaller collection of elements inside a larger ring, but it is not merely any smaller collection. It must be closed under the arithmetic inherited from the larger ring. If we add two elements from the smaller collection, the result must remain in the smaller collection. If we multiply two elements from the smaller collection, the result must remain there. If we take the additive inverse of an element in the smaller collection, that inverse must remain there as well. In plain language, a subring is a smaller arithmetic universe living inside a larger arithmetic universe. For example, the integers sit inside the rational numbers. The rational numbers sit inside the real numbers. The real numbers sit inside the complex numbers. Each is a familiar number system inside a larger one, and each carries its own arithmetic. Polynomials with integer coefficients sit inside polynomials with rational coefficients. Constant functions sit inside larger rings of functions. Diagonal matrices sit inside the ring of all square matrices. Again and again, we find smaller arithmetic systems nested inside larger ones. The next natural concept is a structure-preserving map. In group theory, we studied homomorphisms. A group homomorphism preserves the group operation. In ring theory, we need maps that preserve both addition and multiplication. These maps are called ring homomorphisms. A ring homomorphism sends elements of one ring into another ring in such a way that sums go to sums and products go to product. It respects the arithmetic. It does not necessarily preserve every possible property, but it preserves the two operations that make the structure a ring. This idea is very important. A ring homomorphism is not just a function between sets. It is a translation between arithmetic systems. It tells us that some part of the arithmetic of one ring can be faithfully carried into another ring. As in group theory, two basic objects associated with a homomorphism are its kernel and its image. The image is the part of the target ring that is actually reached by the map. It is a set of all possible outputs. Since the map respects addition and multiplication, the image is itself a ring-like object inside the target. The kernel is the set of all elements that are sent to zero. In group theory, kernels are normal subgroups. In ring theory, kernels are ideals. We shall return to ideals soon, because they are one of the most important notions in all of ring theory. For now, keep the kernel in mind as the part of the source ring that becomes invisible under the homomorphism. The kernel tells us what the map forgets. It tells us which elements are treated as zero. And when we know what the homomorphism forgets, we know a great deal about the quotient structure it creates. Let us pause and summarize. A ring is a setting for addition and multiplication. A subring is a smaller setting closed under the same arithmetic. A ring homomorphism is a map that preserves that arithmetic. Its image tells us what is reached, and its kernel tells us what is collapsed to zero. These ideas mirror group theory, but they carry richer arithmetic content because now there are two operations, not one. Now let us turn to one of the first ways ring theory differs from ordinary arithmetic. In the integers, we are used to cancellation. If a non-zero number multiplied by one number gives the same result as the same non-zero number multiplied by another number, then the two numbers must have been equal. We may cancel the common non-zero factor. This feels natural because we have lived with number systems where it is true. But in a general ring, cancellation can fail. The reason cancellation fails is the existence of zero divisors. A zero divisor is a non-zero element that can multiply another non-zero element and produce zero. That is a strange and important phenomenon. It means that two pieces of non-zero information can combine and disappear. At first, this may feel unnatural. How can two non-zero things multiply to zero? But it happens very naturally in modular arithmetic. For example, in arithmetic modulo a composite number, there may be non-zero residue classes whose product is congruent to zero. It also happens in rings of matrices. Two non-zero matrices can multiply to the zero matrix. It can happen in rings of functions if functions vanish from complementary regions. Zero divisors are not rare curiosities. They are common in ring theory. They tell us that multiplication in a ring may be less reliable than multiplication in the integers. When zero divisors are present, cancellation becomes dangerous. If a non-zero element can kill another non-zero element by multiplication, then multiplying both sides of a statement by the element can lose information. This leads us to integral domains. An integral domain is a commutative ring with a multiplicative identity, where there are no zero divisors. In more verbal terms, it is a ring where multiplication behaves enough like multiplication of integers that non-zero products remain non-zero. The integers form an integral domain. The rational numbers, real numbers, and complex numbers do as well. Polynomial rings over fields are also integral domains. But modular arithmetic only gives an integral domain when the modulus is prime. If the modulus is composite, zero divisors appear. This distinction is one of the first major lessons of ring theory. Some rings behave like the integers with respect to cancellation. Others do not. It is worth repeating the intuition. Zero divisors are elements that break cancellation. Integral domains are rings where this particular breakage does not occur. In an integral domain, non-zero elements do not multiply together to become zero. Multiplication retains a kind of honesty. Why does this matter? It matters because so much algebra depends on cancellation. Factoring depends on it. Solving equations depends on it. Reasoning about roots of polynomials depends on it. Divisibility depends on it. If zero divisors exist, then many familiar arguments must be re-examined. In the integers, if a product is zero, we know at least one factor is zero. In an integral domain, the same reasoning is valid. In a ring with zero divisors, it is not. So integral domains preserve one of the central instincts of ordinary arithmetic. They are not fields necessarily. Division may not always be possible, but they are still clean enough for many factorization arguments. Now let us move toward ideals. Ideals are the true organizing objects of ring theory. At first, ideals may seem less intuitive than subrings. A subring is easy to imagine, a smaller ring inside a larger one. But an ideal is different. It is not merely a smaller arithmetic system. It is designed to be compatible with quotienting. In group theory, when we wanted to form quotient groups, we needed normal subgroups. Not every subgroup works. A normal subgroup is stable enough under the surrounding group operation that the quotient operation is well defined. In ring theory, the corresponding object is an ideal. An ideal is a subset of a ring that is closed under addition and additive inverses, but it also has a special absorption property under multiplication. If you take an element of the ideal and multiply it by any element of the larger ring, the result must remain in the ideal. That absorption property is the heart of the definition. An ideal is not just closed under its own arithmetic. It absorbs multiplication from the outside. This is precisely what makes ideals suitable for quotient rings. Let us say this in a slightly different way. A subring is a smaller place where arithmetic can happen. An ideal is a subset that can be safely collapsed to zero. That is an excellent intuition. An ideal tells us which elements we are allowed to declare equivalent to zero while preserving a ring structure on the quotient. If we want to simplify a ring by treating certain elements as negligible, or as zero, or as indistinguishable, we cannot choose just any subset. The subset must behave well under addition and multiplication. It must be an ideal. A quotient ring is formed by declaring two elements equivalent when their difference lies in the ideal. In spoken terms, two elements become the same in the quotient when they differ only by something we have chosen to ignore. This is the ring-theoretic version of controlled simplification. For example, modular arithmetic arises by taking the integers and declaring multiples of a fixed integer to be zero. The set of multiples forms an ideal. The quotient ring is the system of residues modular that integer. This example is worth holding onto. In modular arithmetic, we do not simply throw away information randomly. We decide that numbers differing by a multiple of the modulus are equivalent. The multiples of the modulus form the ideal. The quotient ring records the arithmetic that remains after this identification. So ideals are the machinery behind modular arithmetic, and quotient rings are generalized modular arithmetic. Let us pause and reflect. A quotient ring is not a vague simplification. It is a carefully constructed arithmetic world. The ideal specifies what becomes zero. A quotient records what remains. And because the ideal absorbs multiplication, multiplication in the quotient is well defined. This is why ideals are essential. They tell us how a ring can be collapsed without destroying arithmetic. Now we can introduce two especially important kinds of ideals, prime ideals and maximal ideals. These ideals matter because they control the nature of quotient rings. A prime ideal is an ideal whose quotient ring is an integral domain. That is the clean conceptual relationship. Prime ideals are exactly the ideals that, when used for quotienting, produce a ring without zero divisors. Let us understand the meaning slowly. In the integers, prime numbers have a familiar property. If a prime divides a product, then it must divide at least one of the factors. Prime ideals generalize that behavior. They detect product structure. They ensure that the quotient does not allow non-zero elements to multiply to zero. So prime ideals are connected to domains. They are the ideals that preserve a no-zero divisor condition after quotienting. Maximal ideals are even stronger. A maximal ideal is an ideal that is as large as possible without being the whole ring. There is no strictly larger proper ideal between it and the entire ring. The quotient by a maximal ideal is a field. This is one of the most beautiful correspondences in ring theory. Prime ideals correspond to quotient rings that are integral domains. Maximal ideals correspond to quotient rings that are fields. Let us repeat this in a quieter form. Prime ideal, quotient is a domain. Maximal ideal, quotient is a field. The ideal tells us what kind of arithmetic survives in the quotient. This is a recurring theme. Ideals are not merely subsets. They are lenses. They reveal hidden structure inside the ring by showing us what happens when we collapse certain elements to zero. If the quotient has no zero divisors, the ideal was prime. If the quotient allows division by every non-zero element, the ideal was maximal. Thus properties of ideals and properties of quotient rings reflect each other. This reflection is one of the guiding principles of modern algebra. It allows algebraists to study a ring by studying its ideals. Instead of looking only at elements, we look at the possible quotient worlds that the ring can produce. Each ideal gives a quotient. Each quotient reveals a different aspect of the ring. In commutative algebra and algebraic geometry, prime ideals become especially important. They behave like generalized points. A space can be studied by studying the prime ideals of a ring of functions. That is a deep idea, but even now, at an introductory level, we can feel its beginning. Ideals encode structure. Prime ideals encode a reducible structure. Maximal ideals encode point-like or field-like quotients. Let us now turn to polynomial rings. Polynomial rings are among the most important examples in all of algebra. Given a coefficient ring, we can form the ring of polynomials with coefficients in that ring. A polynomial is built from coefficients and powers of a variable. But in ring theory, the variable is not necessarily a number. It is a formal object. We manipulate it according to algebraic rules. This distinction is subtle but important. A polynomial is not simply a function, although it may define a function by evaluation. A polynomial is a formal expression. It has coefficients. It has terms. It has algebraic structure. When we add and multiply polynomials, we combine coefficients and collect like powers of the variable. Polynomial rings allow us to build new rings from old rings. If the coefficient ring is the integers, we get polynomials with integer coefficients. If the coefficient ring is a field, we get polynomials over that field. If the coefficient ring is itself a ring of functions, or matrices, or residue classes, we get corresponding polynomial rings. This construction is extremely flexible. Polynomial rings connect algebra to equations. They connect rings to geometry. They connect abstract structure to roots and factors. One of the central operations involving polynomials is evaluation. Evaluation means substituting a particular element for the variable. If we have a polynomial with coefficients in a ring, and if the element we substitute belongs to a suitable ring, then we may compute a value. This gives a map from the polynomial ring to the coefficient ring or to a larger ring. Evaluation maps are ring homomorphisms. They preserve addition and multiplication. The value of a sum is the sum of the values. The value of a product is the product of the values. The kernel of an evaluation map consists of all polynomials that vanish at the chosen element. In other words, it is the collection of polynomials for which the chosen element is a root. This gives a beautiful relationship between roots and ideals. To say that an element is a root of a polynomial is to say that the polynomial lies in the kernel of an evaluation map. Again, kernels are ideals. So roots naturally lead us to ideals. This is one of the reasons polynomial algebra is so central. It unites equations, homomorphisms, kernels, ideals, and quotient rings in a single setting. Let us pause and say that again in more ordinary language. When we substitute a number into a polynomial and get 0, we have found a root. Within ring theory, that simple act is part of a larger pattern. Substitution is a homomorphism. Polynomials that become zero form a kernel. That kernel is an ideal. And quotienting by that ideal captures the algebraic effect of imposing the relation that the chosen polynomial vanishes. This is the beginning of many powerful constructions. For example, one can construct new number systems by starting with a polynomial ring and quotienting by an ideal generated by a polynomial. In this way, algebraic extensions can be built. Complex numbers can be understood through such a construction. Finite fields can be constructed this way. Algebraic number theory uses related ideas constantly. Polynomial rings also connect to analysis. In analysis, polynomials are approximate functions. They define curves. They appear in differential equations and numerical methods. In algebra, polynomials encode equations and factorization. The same object has both analytic and algebraic meaning. But ring theory focuses on the structural side. It asks, what are the ideals in a polynomial ring? When can a polynomial be factored? What are the roots? What quotient rings arise from polynomial relations? What kind of arithmetic does the polynomial ring inherit from its coefficient ring? Now we come to factorization. Factorization is one of the deepest themes in ring theory because it asks whether elements can be decomposed into simple building blocks. In the integers, every positive integer greater than 1 can be factored into prime numbers, and this factorization is unique apart from rearranging the factors. This is so familiar that it may feel inevitable. But ring theory teaches us that it is not inevitable. Unique factorization is a special structural property. It can hold. It can fail. And when it holds for reasons that must be understood. To begin, we need to distinguish between irreducible elements and prime elements. An irreducible element is one that cannot be factored into two genuinely small non-unit factors. In ordinary language, it cannot be broken down in a meaningful way. It may be thought of as indivisible with respect to factorization. A prime element has a stronger property. If it divides a product, then it divides at least one of the factors. This is the familiar prime behavior from the integers. In the integers, irreducible and prime coincide. But in general domains, they may not. This distinction is very important. Irreducible means cannot be factored further. Prime means controls divisibility of products. The prime condition is stronger because it tells us not merely about the element itself, but about how it interacts with all products in the ring. Unique factorization domains are integral domains where every non-zero non-unit element can be factored into reducible elements and where this factorization is unique up to rearrangement and multiplication by unit. In common words, a unique factorization domain is a ring where factorization behaves essentially like it does in the integers. There may be units, which are elements with multiplicative inverses, and units can be moved around without changing the essential factorization. There may be different orderings of the same factors. But aside from these harmless variations, the factorization is unique. The integers form a unique factorization domain. Polynomial rings over fields also do. More generally, polynomial rings over unique factorization domains have good factorization behavior. But not every integral domain has unique factorization. That is one of the sobering lessons of algebra. Even if there are no zero divisors, even if cancellation works, factorization may still fail to be unique. An element may have two essentially different decompositions into irreducibles. Or elements may fail to factor nicely at all. When unique factorization fails, arithmetic becomes more delicate. Divisibility is harder to control. Equations become harder to analyze. Ideals become more important because ideals may preserve structure when elements no longer factor cleanly. This is one of the historical motivations for ideals. In number rings where ordinary elements do not factor uniquely, ideals may still factor in a well-behaved way. This insight was one of the great developments of algebraic number theory. It showed that failure of unique factorization at the element level could sometimes be repaired by moving to the level of ideals. Let us pause and repeat the philosophical point. Unique factorization is not a law of nature. It is a structural property of some rings. The integers have it. Many polynomial rings have it. But other rings do not. Ring theory studies what conditions guarantee it, what happens when it fails, and what structures replace it. Now we approach Euclidean domains and principal ideal domains. These are classes of integral domains with especially strong structure. A Euclidean domain is an integral domain equipped with a division algorithm. This means there is some notion of size or degree that allows division with remainder. The integers have such an algorithm. Polynomials over a field have such an algorithm where degree plays the role of size. The division algorithm is powerful because it leads to the Euclidean algorithm. The Euclidean algorithm computes greatest common divisors. It also gives control over ideals. It is a mechanism for reducing problems step by step. In a Euclidean domain, arithmetic is highly manageable. We can divide with remainder. We can compute greatest common divisors. We can prove that every ideal is generated by one element. This last property leads us to principal ideal domains. A principal ideal domain is an integral domain in which every ideal is principal. That means every ideal can be described using a single generator. Instead of needing several elements to describe an ideal, one element is enough. This is a strong condition. In the integers, every ideal consists of multiples of a single integer. In polynomial rings over fields, every ideal consists of multiples of a single polynomial. These are familiar examples of principal ideal domains. The word principal refers to being generated by one element. A principal ideal domain is a ring where ideals are simple in this sense. Every ideal has one generator. Every ideal can be understood as all multiples of some element. This makes the ideal structure very transparent. Now there is an important hierarchy. Every Euclidean domain is a principal ideal domain. Every principal ideal domain is a unique factorization domain. But the converses are not generally true. There are principal ideal domains that are not Euclidean domains. There are unique factorization domains that are not principal ideal domains. So we have a ladder of increasingly strong conditions. At the top, Euclidean domains have a division algorithm. This gives very strong computational control. Below them, principal ideal domains have very simple ideal structure. Every ideal has one generator. Below them, unique factorization domains have well-behaved factorization of elements. And below them, integral domains merely guarantee that there are no zero divisors. Let us say this slowly. No zero divisors gives cancellation. Unique factorization gives reliable decomposition into reducibles. Principal ideals give simple ideal structure. Euclidean division gives algorithmic control. Each stronger property gives more algebraic power. This hierarchy is one of the central organizing pictures of elementary ring theory. It helps us place examples. The integers are Euclidean, hence principal ideal, hence unique factorization, hence an integral domain. Polynomials over a field are Euclidean, hence they enjoy all the lower properties as well. Some polynomial rings in several variables are unique factorization domains, but not principal ideal domains. This is because ideals in several variable polynomial rings may require more than one generator. That example is instructive. Factorization of elements may still behave well, while ideals become more complicated. So element factorization and ideal structure are related, but not identical. Let us pause and reflect again. Ring theory repeatedly teaches us to separate ideas that coincide in the integers. In the integers, cancellation holds, factorization is unique, every ideal has one generator, and there is a division algorithm. These facts sit together so naturally that we may not distinguish them at first. But in general rings, they separate. A ring may have cancellation but not unique factorization. It may have unique factorization but not every ideal principle. It may have every ideal principle, but no obvious Euclidean algorithm. Each property must be named, studied, and proved separately. This is the beauty of abstraction. It separates familiar arithmetic into its structural components. Now let us revisit the path we have taken, gently and slowly. We began with groups and noticed that one operation is not enough for number systems. Arithmetic needs addition and multiplication. Rings provide a setting where both operations exist and interact through distributivity. We then considered subrings, which are smaller arithmetic systems inside larger rings. We considered ring homomorphisms, which preserve addition and multiplication. Their kernels and images describe what the map forgets and what it reaches. Then we looked at zero divisors. We saw that in general rings, non-zero elements may multiply to zero. This breaks cancellation. Integral domains are rings where this does not happen. They preserve a key feature of the integers. After that, we introduced ideals. Ideals are subsets designed for quotient constructions. They are the ring-theoretic analog of normal subgroups, but they carry the added burden of multiplication. They absorb multiplication from the surrounding ring. Because of this, they allow us to form quotient rings. A quotient ring is a controlled simplification of arithmetic. Certain elements are declared equivalent to 0, and the remaining arithmetic is organized by the ideal. Then we distinguish prime and maximal ideals. Prime ideals produce quotient rings that are integral domains. Maximal ideals produce quotient rings that are fields. Thus the properties of ideals are reflected in the properties of quotient rings. We then move to polynomial rings. Polynomial rings are built by joining variables to a coefficient ring. They are formal algebraic systems, but they also define functions through evaluation. Evaluation maps are homomorphisms. Roots are connected to kernels. Kernels are ideals. Thus polynomial roots, homomorphisms, and quotient rings are deeply connected. Finally, we turn to factorization. The integers have unique factorization, but other domains may not. Irreducible elements cannot be factored further. Prime elements control divisibility of products. Unique factorization domains are rings where decomposition into irreducibles is essentially unique. Then we saw stronger structures. Euclidean domains have division algorithms. Principal ideal domains have ideals generated by a single element. Unique factorization domains have reliable factorization. Integral domains have no zero divisors. These form a hierarchy of algebraic control. Let us now dwell a little more on the intuition behind ideals, because ideals often become the place where ring theory truly begins to feel different from group theory. Suppose we want to solve a problem by simplifying a ring. We may want to impose a relation. We may want to say that a certain element behaves like 0. Or we may want two elements to be treated as the same whenever their difference belongs to a chosen collection. In ordinary arithmetic, this happens whenever we work modulo an integer. We do not distinguish numbers that differ by a multiple of the modulus. We group infinitely many integers into finitely many residue classes. This is a quotient construction. In a general ring, if we want to perform such a construction, we must choose an ideal. The ideal is the set of expressions that become 0. It is the set of permissible errors. It is the set of differences that we ignore. This is a useful way to think. An ideal measures what we are willing to forget. The quotient ring is what remains after forgetting it. But forgetting must be consistent. If two elements are considered the same, then adding the same thing to both should keep them the same. Multiplying by another ring element should also keep them compatible. That is why ideals must absorb multiplication. Without that absorption, the quotient multiplication would depend on representatives, and the arithmetic would not be well defined. So ideals are not arbitrary. They are exactly the right subsets for quotient arithmetic. It is worth repeating, an ideal is a subset that can safely become 0. Now let us connect this again to homomorphism. Whenever we have a ring homomorphism, its kernel is an ideal. The kernel consists of everything that the homomorphism sends to 0. So every homomorphism naturally creates an ideal. Conversely, every ideal creates a quotient map. This is a deep symmetry. Homomorphisms and ideals are two sides of the same phenomenon. A homomorphism collapses some elements. The collapsed elements form an ideal. An ideal tells us how to collapse elements. The result is a quotient ring. This is why kernels matter so much. They are not merely technical objects. They encode the exact loss of information in a structure-preserving map. Now consider prime ideals again. Why should prime ideals produce domains? Imagine a quotient ring formed by collapsing an ideal. In the quotient, a product may become 0. That means the original product lies in the ideal. If the ideal is prime, then one of the original factors must already lie in the ideal. In the quotient, that means one of the factors was already 0. So the quotient has no 0 divisors. This is the prime idea in words. A prime ideal does not allow a product to fall into the ideal unless at least one factor was already there. It prevents new 0 divisors from appearing in the quotient. Maximal ideals go one step further. If an ideal is maximal, the quotient has no non-trivial ideals. In a commutative ring with identity, that forces the quotient to be a field. Every non-zero element becomes invertible. So maximal ideals are associated with the most compressed non-trivial quotient rings possible, fields. Fields are arithmetic worlds where division is fully available except by 0. Domains are arithmetic worlds where cancellation works, but division may not always be possible. Thus maximal ideals give field quotients, while prime ideals give domain quotients. This relationship is simple to state, but it is one of the central organizing principles of commutative algebra. Now let us return once more to polynomials. A polynomial ring is like a laboratory for algebra. It contains formal expressions. It supports addition and multiplication. It has ideals. It has quotient rings. It has evaluation maps. It has factorization questions. When we evaluate a polynomial at a value, we are turning formal algebra into concrete arithmetic, but the formal view is more general. A polynomial exists before evaluation. It is an algebraic object in its own right. This is why two different polynomials may define the same function over a finite field, but still be different as formal polynomials. The formal identity and the functional identity are not always the same thing. That distinction matters. In algebra, the polynomial itself is primary. Evaluation is a map from the polynomial ring into another ring. The kernel tells us what polynomials vanish under that evaluation. If a polynomial has a root, that root gives information about factorization. Over familiar fields, a root corresponds to a linear factor. This is one of the bridges between solving equations and factoring polynomials. Again, we see the same pattern. Roots are about evaluation. Evaluation is a homomorphism. Vanishing is about kernels. Kernels are ideals. Factorization is about breaking algebraic objects into simpler pieces. All these ideas reinforce one another. Now, in factorization theory, it is useful to remember that units do not count as meaningful factors. A unit is an element that has a multiplicative inverse. Multiplying by a unit changes the appearance of a factorization, but not its essential content. For example, in the integers, positive and negative signs can be shifted between factors. This does not create a genuinely different prime decomposition. In other rings, units may be more varied, but the idea is the same. Units are reversible elements. They are algebraically harmless in factorization. So when we say factorization is unique, we always mean unique up to order n units. This caveat is not a technical nuisance. It is the correct way to state the idea. Factorization is about the irreducible content, not about reversible changes. Now consider irreducible elements again. An irreducible element cannot be decomposed into two non-units. It is a building block in the sense that it cannot be broken further. But it may still fail to be prime. That is, it may not control divisibility of products. This is one of the places where abstract algebra becomes subtle. In the integers, every irreducible is prime. So we may be tempted to treat the two words as synonymous. But they are not synonymous in general. Prime is a stronger, more global property. Irreducible is a local factorization property of one element. Prime is a statement about how that element interacts with arbitrary products. Unique factorization domains restore much of the familiar integer behavior. In such domains, irreducibles behave well enough to support unique decomposition. Prime elements and irreducibles are closely tied. Divisibility becomes manageable. But when factorization fails, ideals often provide a more stable language. This is one reason ring theory does not merely study elements. It studies ideals. Ideals can capture divisibility in a more flexible and robust way. Now let us revisit the hierarchy one last time in a slow and careful way. An integral domain gives us a ring where multiplication has no zero divisors. Cancellation is safe. This is the first level of arithmetic reliability. A unique factorization domain gives us reliable factorization into irreducibles. It tells us that elements can be decomposed in a controlled and essentially unique way. A principal ideal domain gives us reliable ideal structure. Every ideal is generated by one element. This means ideals behave much like divisibility by a single element. A Euclidean domain gives us a division algorithm. This is stronger still. It gives an effective process for computing remainders and greatest common divisors. So each step adds control. Integral domains control zero products. Unique factorization domains control factorization. Principal ideal domains control ideals. Euclidean domains control division and computation. The stronger the ring, the more familiar its arithmetic becomes. But the weaker structures are not failures. They are simply more general. Many important rings are not Euclidean. Many are not principal ideal domains. Some are not unique factorization domains. Some even have zero divisors. Ring theory gives us language for all of them. This flexibility is one of its strengths. It allows us to study integers, polynomials, functions, matrices, modular systems, coordinate rings, and many other algebraic worlds under one conceptual framework. Let us now move toward a final unifying summary. Ring theory begins with the recognition that arithmetic has two operations. Addition alone gives group-like structure. Multiplication adds richness. Distributivity ties the two together. Once we have rings, we naturally study smaller rings, maps between rings, and the elements that maps collapse. Kernels become ideals. Ideals make quotient rings possible. Quotient rings express controlled simplification. Zero divisors tell us that not all rings behave like the integers. Integral domains recover the cancellation behavior that we often rely on. Prime ideals and maximal ideals show that ideals are not passive subsets. They encode the nature of quotient arithmetic. Prime ideals give domain quotients. Maximal ideals give field quotients. Polynomial rings provide a universal arena for algebraic expressions. Evaluation maps connect formal polynomials to roots and functions. Kernels connect roots to ideals. Factorization connects polynomials to divisibility. Unique factorization domains tell us when the familiar prime decomposition of the integers has an analog. Euclidean domains and principal ideal domains explain stronger forms of control, from division algorithms to simple ideal structure. And throughout all of this, we return to the same quiet theme. Ring theory is generalized arithmetic. It is the study of how addition and multiplication behave when we loosen the assumptions of ordinary number systems. Sometimes familiar rules survive. Sometimes they fail. Sometimes they fail in instructive ways. And when they fail, new structures, especially ideals, help us understand what remains. Let us pause and reflect one final time. A ring is a world of arithmetic. An ideal is a way to simplify that world. A quotient ring is the simplified world that results. A domain is a world where multiplication does not create zero unexpectedly. A field is a world where division is available. A polynomial ring is a world where formal algebraic expressions live. A unique factorization domain is a world where decomposition into basic factors is reliable. A principal ideal domain is a world where every ideal has one generator. A Euclidean domain is a world where division with remainder guides the arithmetic. These concepts are not isolated definitions. They are connected stages in our understanding of algebraic structure. The more we study rings, the more we see that ordinary arithmetic is both familiar and special. The integers are not merely numbers we learned as children. They are an example of a remarkably well-behaved ring. Polynomials over fields are similarly well-behaved. But the universe of rings is much larger, and in that larger universe, each familiar property must be earned. So as we rest with these ideas, it is helpful not to force every detail at once. Let the ideas settle. Rings have two operations. Ideals allow quotients. Domains avoid zero divisors. Prime and maximal ideals control quotient behavior. Polynomials connect formal algebra with roots and factorization. Unique factorization is a structural gift, not an automatic law. Euclidean and principal ideal domains show how strong arithmetic order can become. And with that, we have traced a gentle path through ring theory and polynomial algebra, from the motivation of two operations, through ideals and quotient rings, into domains, prime and maximal ideals, polynomial evaluation, and the layered structure of factorization. All of it is one long meditation on arithmetic. Arithmetic made abstract. Arithmetic made flexible. Arithmetic understood not as a list of computations, but as a structure whose hidden patterns can be named, compared, simplified, and studied.